this short presentation, I'm going to give you some information about how the kidneys work in our body and how we try to mimic their function with hemodialysis. I will talk about why the kidneys are so important for us. And the kidneys really are a dynamic filter, and they make sure that our body is in balance. And they do this by filtering out bad compounds such as toxins, such as waste products. But besides that, they also make sure that our electrolyte levels are in balance, that they level out the amount of fluid, so that's how you can keep your blood pressure in check. And then they also produce some compounds that are used to promote the formation of red blood cells. And if your kidney doesn't work quite as well as it should, then people receive a type of dialysis treatment. So this can be in your body as well, but you're probably more familiar with hemodialysis, which occurs with a machine outside of your body. Now, the structural and functional units in the kidney that actually facilitate this filtering, that's what they call the nephrons. And in each kidney, you've got about 1 million to 1.5 million of them. Up to any point in time, they can hold up to 20% of your total blood volume. So they have a tremendous throughput throughout the day. And the picture that you see here, this is more a picture that you would see in a textbook for medicine. So how would it work? So what I will do instead in the next slides, I will go through it from an engineer's perspective to kind of break it down on what you see. But the reabsorption step is really important as well. So if you look at the anatomical structure, you will see that you've got these large loops, and from an engineer's perspective, that means there's a lot of surface area, which is important for this reabsorption to take place, which is driven by osmosis. So let's just break this down into streams that go in and that go out. So let's break down what that actually means in terms of the streams. So you've got something coming in, and then you've got a filter there. And you will see in that filter actually 99% of the compounds will actually go through. The compounds that are much bigger, so for instance you've got red blood cells which are micron size, they can't pass through it. So the other 1%, and you will see what it's in the next slide, you'll see these are the bigger compounds, so everything which is more than a few nanometers, so such as red blood cells, white blood cells, but also proteins that have a negative charge. So about 1% is then circumvented and 99% goes via this filter. But even though 99% actually passes through the filter, here you will see how important this reabsorption process is, and particularly for water. So around 70% is being reabsorbed again via osmosis. And this is particularly important because otherwise you would lose too much water. Now, what's then being reabsorbed again goes back into the vein, back into your heart, and all the compounds that need to be excreted, they go out via your urine. But let's look into a little bit more detail what this filter, and we look at the glomerular space. What does this look like? You will see here in this slide, this is more the physiological picture. So you see it's like a slit diaphragm. So there are certain holes where the molecules can pass through. And if we break it down, we can see there's actually 4 different steps that they go through. So first of all, you've got these little capillaries, which are called fenestration ports. Then you've got a membrane, which is again broken down into different layers. Then we've got something which looks a little bit like feet, so that's why they call it podocytes. And then you've got a small protein as well, which is nephrin. So breaking that down into what can actually pass through those. The first step when you look at the capillaries, so you see that only compounds, and these are leakier than your normal capillaries in your blood, compounds that are between 50 and 100 nanometer, they can actually pass through. The next layer, so this is where we have a membrane which again consists of 3 different layers. So it has something negatively charged on the outside, and you'll see that's really important, it's heparin sulfate. Then you've got collagen, and then you have another layer of heparin sulfate. So this negative charge means it can actually repel proteins with a negative charge. And most of your blood proteins, such as for instance albumins or fibrinogen, they've got a negative charge. So while they might be quite small, so if it wouldn't be for the negative charge, they can actually pass through. This particular membrane will make sure that they're being diverted. So in the initial stages of kidney failure, you will actually see that you can find lots of these small proteins, such as albumins. You can find them back in the urine because it kind of becomes leaky and it can pass through the system, which is what you don't want because it causes inflammation. Then again, you've got another layer, and you will see this is not like a full layer, so there is some kind of spacing between them. So anything which is 20 to 30 nanometer, make sure that it kind of gets captured there. And then in between those, you've got a little protein layer, which is where only compounds of about 7 to 9 nanometer can pass through. So by having this layered structure, you can make sure that you can pick out the compounds and you can kind of trap them in different parts. So even as one part is not working, you've always got a type of backup system. So you can express your kidney function as a type of filtration rate, so that they call the glomerular filtration rate, or GFR. So when that starts to go below 20%, that's when you might want to start thinking about using dialysis, because you would get like a build-up of the different toxins in your blood, and also you would get issues with swelling and nausea. And actually what I didn't know is that dialysis is not so easy to prepare. So there are like shortcuts that you can take, but in order for this to work, you would often monitor this filtration rate over time. And you would need to make a connection between a vein and an artery in your body. So this is a quite minor procedure, but it can take months to heal. So usually there's like a process of around 6 months where they have to prepare this in order to make sure that they can actually dialyze your blood. What then happens is the machine draws the blood coming from your body, and then it's passed in counter current versus a dialysate. So you've got two opposite streams working. And this is very important because that means you maintain a concentration gradient over the full length of the dialysis machine. So this makes the exchange much more effective. And it works by having a semi-permeable membrane. So you've got lots of different membranes that would have particular pore sizes, and only the compounds that you want to filter out will be filtered out. But if you compare this to the kidney, so here we're working with a filtering system. The kidneys you can better describe as a dynamic filter, because you've got both filtration and reabsorption. So when you're doing the dialysis, you're actually only looking at the filtering. And you will see that this can have some problems. Obviously, dialysis has got some main problems associated with it. The first thing being that it's very time consuming, so you would need to go, either you could do it at home or at the hospital, so several times per week. So you're kind of limited in what you can do. And then because you would be connected to something, so you're inserting a tube in your body, there's always a high risk of infection associated with it. So particularly older people don't tolerate this very well. If you look at this picture, you will see that the vein and the artery are connected. So you've got blood coming out, it's pumped, and then you add an anticoagulant to make sure that it doesn't clot. Then it actually goes in the machine where you will see the dialysate is added. But what's also very important, and what you can see here, is that there's a problem with the water, so water needs to be added as well. So think back of the kidney where it had like a very dynamic function. So it had both the filtering and the reabsorption. And this reabsorption process is so important to regulate water levels in our body. And that seems to be what we can't mimic with a dialysis machine. So if you would be on dialysis, you would have to restrict your fluid intake. Now we go through this process where you filter out the toxic waste compounds, and then before it goes back in your body, you will also see that there's a bubble trap to make sure that there's no oxygen that can go back in your blood. Because as you all know, the oxygen can travel through your body and it can also lead to dangerous situations. So what we've seen here is that the kidneys are very complex. It's not just the filtering, the reabsorption is a very important part of it. And while we seem to be doing okay in mimicking the filtering aspect of a dialysis machine, this reabsorption we haven't quite gotten to grips to how this works. So hopefully with this short presentation I've broken down from an engineering perspective how the kidneys actually filter out the toxic compounds from our body.